uh, poor Justin. He was, he's the best. He's the interim champion, and Khabib Nurmagomedov is so much better than him that he kind of toyed with him here. Anyway, I just find it interesting. So, do you guys want to talk about chemistry now, or would you like to complain about the long exam? Everybody turned it in. That's really good. I'm super happy everybody turned it in. So everybody gets a good grade already, I think. Hey, Richard. We were just watching Justin Gaeta and Khabib Nurmagomedov.
I saw that. It was pretty awesome. And I
Yeah.
heard Habib became an analytical chemist after he retired.
That's right. That's right. Well, everybody's got to move up in the world, right? Oh God. Oh my gosh. Okay. So I'll just dive in from here because everybody's like so bored with all this. But I'd like to talk about lead-free, or no, let's talk about perovskite solar cells right now, right? And so perovskite it's a well-known crystal structure basically, and it's like ABX2, or I forget the. Let me look it up. It's AB. How is the perovskite structure? Perovskite is ABX3, right? So calcium titanate is one, and basically they have these pyramidal structures, and so it's a very vague sort of a classification of materials, but it works with these. They're called. Well, I'm not exactly sure what they're called. Here's a halide double perovskite, whatever that means. But the perovskites that are of the most interest right now are tetramethylammonium lead iodide. And so it's like tetramethylammonium 2 lead and then 6 iodides or something like that. And and you can make films of them. Let's see here. There's organic inorganic halide perovskites such as CH3N8, NH3. So that's methylammonium lead iodide. So this molecule, you can cast films of this molecule onto a surface, and if you do it right, then it will be a semiconductor, and then you can sandwich that semiconductor between appropriate contacts and then shine light on it, and it will give you current back. It'll make energy. And so that was a pretty big deal because they're already up in the 20 in the greater than 20% efficiency range. That is that more than 20% of the light that falls on the perovskite will actually be converted into electrical power. And so I wanted to talk about that a little bit, but as a way of introducing it, I'm going to give you guys a little talk from one of my archives on basically on solar cells. So let's talk about solar cells briefly here. And this was a talk I gave to Balaz Analytical. I worked there one summer, and I worked on solar stuff for him. Um, and this is my talk, the Balaz Analytical. Let me actually go ahead and make it full screen, and I can walk through it here. So obviously, they're wanting to do analysis for the solar energy sector, so I was working on that for them, but not that it came to anything. So this is me, and I actually did my PhD in molecular electronics. So it's, it's really, so it's not that, so solar cells and whatnot are not that far from my training, my basic training, but I never trained with real semiconductors, so it's interesting. So I know enough to be dangerous, like with most things. And then I postdoced at Illinois. Now I'm here, da da da. And so any photovoltaics, the motivation for using them is so that we don't have to burn so much oil, right? But there's a lot of oil on the planet, right? So I don't think it's going to run out, real soon. But nobody really knows. And if it does run out, it's the shock to the world system could be really, really severe. Can you imagine no electricity, no water, no fuel for transportation, no fuel for agriculture, these types of things. It could be a major shock if it ran out suddenly. And so this is the number of barrels per day of oil that we use, that the world uses. 100 million barrels per day, with and that's about 60,000 gallons per second, and that comes out to about a cubic mile every year, right? So this is downtown Indianapolis. I don't know why they use Indianapolis, but this is the map of downtown Indianapolis, and this is a cubic mile on top of it, and that's the amount of fuel that the world uses every year. The amount of oil fuel, right? So it's not an insignificant amount, and it will eventually run out. We've been doing this for many years now. So there's the Earth, right? And there's a lot of square miles, so there's a lot of places to look for oil, but it's not everywhere, that's for sure. And if we look at the mixture of all these different types of power sources that we use over the years, basically oil and natural gas have been on the rise. But there's consequences to burning oil, and one of the main ones is that it's increasing CO2 levels in the atmosphere. So one of the things about atmospheric CO2 is that human fossil fuel burning, right, anthropogenic CO2, is not the main source of CO2 in the atmosphere. The main source is the respiration of animals and the so the biological and the abiological breakdown of organic materials. So like burning, any forest fire or whatever, and any non-biological breakdown of organic materials, plus all the organic respiration, that type of breakdown, it actually creates a flux of CO2 into the atmosphere that's quite a bit larger than the flux from human burning of CO2. It's just that the CO2 that we burn is in excess of this balance, right? And so, we're not we're not doing it all from plants where the plants grow, and as they grow, they absorb CO2. Then as they decay, they release it back into the atmosphere. We're actually adding to the total mass of CO2 in the air because we take these deep wells of sequestered hydrocarbons and we burn them and we create excess CO2 that way. Although in any given year, the total flux from humans is smaller than the total flux from the burning of biomass, right? Or the respiration and burning of biomass. So right now, this was probably 2015 data, and you can see that oil has come down, gas has come up, coal has come down, but they're still the major parts. And hydro and nuclear are there, and then all the renewables together, they're probably closer to 2% now, but still they're not a major part of the energy equation. But they're growing very quickly, And here's a nice GIF that this is an up-to-date one. This goes to 2019. You can see that solar is still a very small little sliver here. And, there's gas, and then all the renewables are up here, just in the upper right here. We've got gas, oil, coal, and traditional biomass, which is like burning wood and other stuff like that. So then this is interesting because this was quite old, This was when this study was done, and they were trying to project the oil price, right? And of which of these three do you think is most likely what we have today?
The red.
The red. Actually, that's a good guess, but it's actually closer to the blue here, because there's been a lot of every time there's a depression, like COVID-19 has pushed the use of oil way down, the use of transportation fuel. So the cost of oil is below $60 a barrel right now, I think. I could be wrong. But anyway, so so one of the questions is can solar take a large chunk out of this equation? I think it can, and it depends a little bit on kind of what data you believe, I guess. But according to Matthias Loster of the physics department at UC Berkeley, if you covered these black disks on the globe with solar cells, then you could power the entire world with solar photovoltaic. But I'm not really sure. I mean, this also assumes that there's an enormous amount of battery backup, something we haven't seen so far, because obviously you need to store the excess power during the day and discharge it at night, So there's a fair number of assumptions here. But one of the good things is that when you think about the economics of photovoltaics, is that from cradle to grave, if you start with just mining silicon and a little bit of silver and aluminum and all the ingredients that you need to make a solar panel, right? From the mining of the materials to the refining and the manufacture and the installation, that's all the cost of putting this thing into the grid, right? And right now that cost comes out to about $3 per watt. And that's actually installed residential. That's not commercial. That's residential, right? and then those panels will produce power. They're guaranteed to produce power for 20 years now. That's an industry standard. Oh, $39 per barrel. Wow. Wow. Yeah, that's wild. So uh so uh so what happens then is, it costs $3 a watt to make it, but then it produces, um that watt of power, it produces it for 20 years. So if that's, you know, uh, say it's 10 hours a day, that's a ton of watt hours. I'm not going to try to do the calculation. It's a ton of watt hours, right? And so if the if you in your mind you advance the world to a point where we had enough photovoltaics to power everything, something like this graphic, but obviously they wouldn't be so concentrated in small areas, etc. But if we had enough photovoltaics to power the planet, then we could make more photovoltaics with just a tiny fraction of the lifetime energy output of these photovoltaics. It's about 2% of the total output of these photovoltaics. We could make more photovoltaics, and then we could recycle the existing ones when they're dead. So it's a breeder system that's very, very viable. And so anyway, I'm sort of going on and on about this, but there's no serious downside, to this, and it's coming. May not be in my lifetime, but probably by the time you guys are getting around to being retired, we'll probably have 20% of the world's energy supply coming from solar and wind. Probably there'll be more nuclear too, but who knows? So so here we were in 2015, and in 2020, which is where we are now, this says we should be around 2%. So in that 5 years, we've probably doubled the amount of energy. Well, maybe it's more like 4 years. In that 4 years, we've doubled the amount of energy as a fraction of the total energy production that we get from photovoltaics. And this extends way into the future, but at the time it was done, it was more like 2015, right? And they just drew this line, and as far as I know, this is about right. We're coming up around 2% now, I think, from photovoltaics. Maybe not, but we'll see. Maybe we're a little bit shy of that. But that is on the heels of the declining cost of photovoltaics. And so this is on the way to $1 per watt. And this only goes back to 2006. But now the cost of this is the cost of the cells, and they're about 60 cents per watt per cell, right? Which is amazing. And these are 20% cells, 20% efficiency, and 20-year lifetime cells. So it's very, very encouraging, in terms of all of our futures, and our children's futures, is that this is a technology that can work, So in any case, that's pretty cool. And PV has been growing like crazy, and this is now these are literally in gigawatts now. So this is only back to 2006. Oops. And then this is just different companies that make it. Sharp, Q-Cells, Kyocera, Suntech, Sanyo, Mitsubishi, Motec, Schott, Solar, BP Solar, Solar World, and others. So this is what I told Air Liquide. And, basically, they do analysis. So we were interested in analyzing silicon all the way from, the raw material all the way to, basically the wafer, possibly the cell level. And so the photovoltaics themselves they're like sandwich structures that absorb light. That when it absorbs light, it makes electron hole pairs. The electron holes are collected. The electrons and holes are collected, and the current is directed to an outer circuit, and power is generated. Right. So here is my cartoon of a photovoltaic PN junction. Right. And here you have boron doped silicon. So every intersection here is a silicon atom, right? And this is just a 2D arrangement, right? It's silicon actually has the diamond structure, so it's a little more complex. But if you substitute some borons in for silicons, then the boron will become tetravalent, and it will actually have an extra electron donated from the lattice, the valence lattice of electrons, right? And that will actually leave behind a hole in that lattice of bonds that make up the silicon. And that hole can move around, right? And a lot of times these, so this is p-type silicon. And p-type silicon has many holes in the valence band, and the holes are permanent. They're there permanently, right? So p-type silicon can conduct by the movement of holes through the bulk of the silicon, right? And the same is true of the n-type, except the n-type, you substitute, this is a group 3 atom, silicon's group 4, and then phosphorus is group 5, and it will have 5 valence electrons. So when it assumes the tetravalency of the lattice, it will dump an electron into the conduction band of the n-type silicon, right? So these are actually fairly high energy electrons, and these are fairly low energy holes, right? And so the electrons that are there in the n-type, if it's, substitutionally p-doped, or I'm sorry, n-doped silicon, it will have these electrons. The electrons will be in essentially a big anti-bonding orbital, the collective anti-bonding orbital of the silicon. And then when you put these when you place these electron and hole doped type materials in intimate contact, it creates what's called a PN junction. And in that junction, some of the electrons from the n-type and some of the holes from the p-type have annihilated, right? So that means that the electron filled the hole, right? But that happens because it can happen. It's an entropy-driven process, mainly, and but it leaves a negative charge on the p-type silicon and a positive charge on the n-type silicon, right? Because the n-type silicon lost an electron, the p-type silicon gained an electron, right? So there's a spatial inhomogeneity in the charge balance, right? So the charge overall in this box is still neutral. But on the left side of this box, there's 2 negatives and 1 positive. And on the right-hand side of this box, there's 2 positives and 1 negative. So this means that at the junction, there's an electric field, right? And that's it's sort of normal. It's like a big old, it's like a dipole moment that happens at the interface between these two materials. And the weird thing is that they conduct electricity, but there's this depleted region here, right? Because this guy can only conduct using holes, this guy can only conduct using electrons. When they annihilate in this region, it depletes of carriers, so that this region here is not that conducting, and then there's an electric field across it, right? So now when light comes and strikes near this region, what'll happen is the holes will be swept to the left and the electrons will be swept to the right by this pre-existing potential here, right? And then then they can recombine externally, right? Now, obviously, if they recombine here, it's not good for the solar cell, right? That's called recombination. So let's see if we can, I'll just run these little simulations again so you can see. The excess holes on this side migrate, the excess electrons on this side migrate, they annihilate and they leave a charge behind. Then a photon comes in, creates an electron hole pair. The electron hole pair is swept apart by the electric field, the pre-existing electric field here, right? And then that is collected and it does some work externally, right? So that's really all it is. So in a typical solar cell, in a silicon solar cell, there's a thin N-type layer and then a bulk of P-type silicon. And then when an electron hole pair is created, hopefully they get separated by the field here and then recombined externally. This is just sort of a little bit more detail and whatever. But and then the anti-reflection coatings kind of darken the surface a little bit. It's another sort of a interesting area of research is how to get less light to bounce off, and more light to go in. But there's various types, there's copper, indium, gallium, selenium SIGs is a fairly it's not really popular anymore. At the time that this was done, it looked like it might become the type of photovoltaic material. And there was a startup called Solyndra which got $50 million from the government and provoked howls from the GOP at the time, and but they ended up going belly up. Oops. And but now most photovoltaics are made with single crystal silicon. So sputtered silicon didn't work. Multi-crystalline silicon, it works okay, but single crystalline silicon works the best. And single crystal silicon is by far the most efficient, And $1 per watt is supposed to be parity with the grid. And I think for commercial, for large photovoltaic farms, they're about at parity right now. And as the silicon gets cheaper and as these big facilities go up, it's funny, you think, oh, the photovoltaic places would be making money hand over fist. But actually, it's not true because there's a tremendous amount of competition in that sector. So, But silicon's not a really good semiconductor for this purpose. It's not intrinsically good because the absorption coefficient of silicon is relatively low, and um, it's because of the crystal structure of the silicon makes it indirect, so that it's kind of like a forbidden transition, the absorption of light by silicon to make electron hole pairs. So it's weak, basically. Other semiconductors like the cadmium selenide and SIGs, the copper indium gallium selenide, and the perovskite ones that we're going to look at, they're actually called direct gap, and they absorb much more light in a very thin layer. So that, it's, you can just use a thin, like a coat of paint. You can just paint them on and make contacts on them, and that's all you need to make a solar cell with them. So the amount of material used is very low. On the other hand, silicon is it's highly abundant. I mean, it's the second most abundant element in the Earth's crust. So it's like no problem there. So right now, most silicon photovoltaics are made by sawing. You saw the wafers off of the boule, off a big old sausage of silicon that comes out of a vacuum furnace, and then you cool it down, then you saw the wafers off the end. But anyway, I'm not going to talk about this stuff. Sunfab is kind of interesting. This didn't really go anywhere. The Applied Materials made Sunfab to make these sputter deposited photovoltaic cells, but they're not efficient enough to compete with the single crystal cells. So I don't know. Maybe they're using them in the farms, but I just don't know. So single crystal silicon is where it's at, right? And there's various relative costs, but anyway, but hyper pure single crystal silicon is where it's at in terms of cost right now, right? So there are poisons for silicon, and the poisons, obviously phosphorus would be a poison, right? Because that's an N dopant, right? And then you've got all these different metals that can dope or cause defects or otherwise spoil the photovoltaic efficiency, right? So from a baseline efficiency of 1, it only takes 10 to the 12 atoms per cubic centimeter of tantalum to cut the efficiency to 60%. So 10 to the 13th atoms per cubic centimeter. Remember, that's about 1 in 10 to the 7th atoms of tantalum, right? So it's about a tenth of a part per million. So 100 parts per billion of this guy. You can get more of some of these others, but still, you have to be able to measure a lot of elements very sensitively in order to analyze pure silicon, So ppm atomic, here it is. Oh, this is 10 to the minus 5 parts per million. So that's really low. So this is 1 part per billion right here. And this is going to be 10 parts per trillion. So anyway, so you can see that the analysis of silicon is actually really challenging. You can get a bunch of silicon, and then question is it pure enough to throw into your furnace and melt and pull, right? And if you throw impure silicon in there, it's a big problem. So one of the, as opposed to doing all this detailed analysis, what is more typically done is they look at the lifetime of electron hole pairs in silicon. So if you basically you can do it in different frequencies, but you look at you have a little light that'll flash onto the silicon, and then you measure the conductivity of the silicon as a function of time. And if the conductivity disappears instantly as the light goes off, then you know that it's impure. But if there's conductivity for a couple of seconds, a couple of milliseconds after you turn the light off, then you know you've got pure silicon, and that's a phenomenological way of assessing the purity of silicon, the suitability of that silicon for photovoltaic devices. So anyhow, I go on, and here's a typical melt processing, right? Is this is how you make the hyperpure silicon, right? Is you start with the feedstock for these is actually silane, SiH4, or it could be chlorosilane, SiCl4. But both of those are monstrously explosive pyrophoric reactive materials, right? The thing is, you start with sand, right? And sand is terribly polluted stuff, And then you react it with hydrogen or chlorine or whatever, and you get gas phase silanes coming out, right? And it just leaves all of those metals behind. And so then you recondense the hyperpure silane, right? And then you have to go through another process to get the oxygen or the hydrogen off of the silane, SiH4, so that you just have Si left over, and then you melt that in one of these crucible furnaces, and then in the tip of you take a single crystal of, it's called a seed crystal of silicon. You touch it to the top of the molten silicon here, and then you start to cool. You start to pull up on that wafer, and then what happens is that this is just right near its melting point, right? And the air around here is relatively cool. So what'll happen is you can, from the point where the crystal touches it, that determines the crystal structure of all of this silicon that's condensing all around it, right? And you just slowly pull it up. You pull and pull and pull. And then it creates what's called a boule. And the boule is it's a big old huge monolithic single crystal of silicon. And then once you get this boule, then you saw it into wafers. And I'm sure it's a fascinating technology all on its own, But that's how you seed these single crystals from the molten silicon, and that's how you get that. So so I thought I was pretty smart, and so I I was looking at these advanced ways of mapping out the traps and all the problems in photovoltaics, right? And this is, I don't know exactly how this is done, but what they did was they would probably pulse a light source, and then then you can map out the regions where the carrier recombination is slow or fast. You know, and they used 880 nanometers. That's an LED wavelength. You know, and uh, so are you guys still kind of with me in terms of what carrier recombination means? Maybe you could put a comment um, in the box here. Oops. So a carrier is an electron or a hole. And when the carriers recombine, that means that they're liberated from each other basically by the light, and then they typically orbit each other for a little while, and then they recombine. And there's actually different sort of states in their existence that they go through, right? You can have really free holes and electrons. Then you can have excitons, which are holes and electrons that are orbiting each other. That's a slightly lower energy state, electron hole pair. And then there's another thing called a polariton, but I'm not really sure what that is in this, particularly in this context. But so you can have free carriers and polaritons, and then they can recombine. And the free carriers are the ones that are useful for photovoltaics, and they create conductivity. Now, their existence makes the silicon conduct.
So is recombination not wanted?
Right. Yeah. Recombination is not wanted.
So does that also have to do with the efficiency and why it's like 20%? Or is that something else?
Exactly right. Exactly right. Yep. Yep. The efficiency of, I think, most silicon is governed by recombination kinetics. And there's another kind of an interesting aspect to that, which is where the absorption maximum of the silicon is relative to the solar maximum of the emission from the sun, right? And they're not perfectly matched, you know, but it's not terrible, but it's not a perfect match. So if you want to make a really efficient solar cell and you don't care how much it costs, like you're going to send it to space or something, then what you can do is you can make multi-junction solar cells. So you'll make a layer of gallium arsenide and a layer, you know, of something else and a layer of silicon, and they'll each layer will absorb a different wavelength, create electron hole pairs, collect electron hole pairs, hopefully, you know, and then uh, I'm not exactly sure whether they just sum up the voltages in those processes or whether they're somehow wired in parallel. But the multiple junctions mean multiple semiconductor types, so that you can match the emission from the sun to the absorber that you have in silicon, or in the photovoltaic rather. So how's everybody doing with this? You doing okay? Adichie, you doing okay?
I think so.
Okay. So, I mean, the reason I'm talking about this is that these are all concepts that are going to come back up in the perovskite solar cell paper, and so I hope that it's informative for you in some way. Um, uh, but yeah, so carrier recombination is important here, right? And to to measure these types of impurities, one thing that's done is called X-ray fluorescence, and to do X-ray fluorescence, there's a whole bunch of different there's a number of variants on it, but a lot of times it's resonance fluorescence. I'm not exactly sure which technique is being used here, but this was probably done at a synchrotron, right? And they took silicon that had a high recombination rate and silicon that had a low recombination rate, and they looked at the amount of chromium, iron, and nickel impurities by the presence of fluorescent X-rays at these energies. So it's a little hard to see, but the low recombination has essentially zero, has on this scale an essentially zero background count for chromium, iron, and nickel, right? But the high recombination silicon has chromium, iron, and nickel clearly, and so this is probably from a single wavelength excitation, and this is the emission spectrum. So you guys remember from the first paper we studied, right? The emission spectrum is where you have a single wavelength going in, and it's a higher energy than anywhere you're looking. And you look on the red side of that and you run a scan. You see if the material is down converting and re-emitting these photons. So this is most likely this is an emission scan, and there's probably some 10 or 20 keV photons coming in, and then these are looking out. But this was also done in a synchrotron. So a synchrotron is a sort of it's a particle accelerator. They use typically billion electron volt electrons in a storage ring, and it's actually typically it's an octagonal storage ring, and at each place where they bend the path of the electrons, they do it with these big permanent magnets. The electrons kind of slam into the magnetic field and they make a left turn. And then as they do that, they just shoot out a bunch of X-rays. And so at each point in the storage ring, you have this really, really bright X-ray source. And all you got to do is take the cap off, there's a window. You can uncover the window and you've got all these X-rays coming out, and then you can measure stuff using those X-rays. So, but they're not cheap, and there's even in the Bay Area, there's I think only 2 or 3. There's one at Stanford, the Stanford Linear Accelerator at SLAC, and there's one in Berkeley, and not sure where the third one is, but pretty sure there's a third one in the Bay Area. But then there's others throughout the U.S., but just a few more. And then there's a few in Europe and in Japan. But so this is a difficult way to do it, but it can be done, right? And it's interesting that even with a synchrotron, it's hard to find the iron, right? But then if you do this type of thing, right, you can you can take just a tiny little um, focused beam or even collimated beam of X-rays, and you can pass it in this 200 by 300 micron area and scan it around, and you just count the number of X-rays that come as a function of position, right? So where the X-ray hits the wafer, you can see, you can localize these defects that are full of iron and nickel, right? And in this case, it's actually this black box was then analyzed, and you can see that there's, if you look at the iron distribution and the nickel distribution, they look very, very similar. You know, the iron has some stuff here, whereas the nickel doesn't. But otherwise, the nickel is the little brother of the iron here. So they tend to come together, and they tend to be segregated in this way. So it's information, but it's not necessarily a solution. But it's interesting too, because it's not homogeneously distributed, right? I mean, there's probably hyperpure silicon here, but on this, if on a 300 micron scale it's contaminated, it's probably not it's not of any use. So anyway, that's it for that talk, right? And so what we should do for next time is have a look at, this is, it's called 2A, should be called 5A, right? Because we're in paper 5. This is paper 2 from 2017 when I taught this, but this is paper 2A by Justino and Snaith, these English fellas, and they're talking about lead-free perovskite, or toward lead-free perovskite solar cells. It's in an energy perspective journal, but it's good chemistry, it's good analytical and physical chemistry, and they talk a lot about making variations on the normal methyl ammonium lead iodide, MAPBI3, and how those changes are used. They're kind of rationally trying to make it more stable. They're trying to use metals other than lead, right? But it's actually pretty difficult. And if you look, for example, at, let's see here, where's my periodic table? There you are. Look at the periodic table. Lead and tin, germanium, they're all group 4, They're not transition, lead is not a transition metal, nor is tin or germanium. They're all in this carbon group here. And tin has its problems. Lead and tin iodide are both real toxic, And so there's problems with, there's possibly insurmountable problems with this type of technology, And for all the hype, for all the good things, right? You can say about the perovskites, there's just a couple little problems, and that can completely ruin them. It can completely torpedo them for their use in any practical No, Google, I'm not talking to you. You have to be polite with your telephone sometimes. So So there's just, you know, has to do so many things so well, you know, and it's like a drug discovery, you know. For every million drug candidates, you get one that makes it to market, you know. So but methyl ammonium lead triiodide is it's a direct gap, meaning it's a strong absorber of light. Has a band gap of 1.6 eV, so that puts it in the red, I think. And um, it's near the optimal gap for single junction solar cells. So 1.43 that's just like the solar maximum in output, and 1.6 is close to there, right? So then you know, it's 25 times better absorber than silicon. It's even better than gallium arsenide, which is pretty good for this type of application. It's got a sharp onset, has long-lived electron-hole pairs, and the electron-hole pairs diffuse a long way, a long distance. Remember that this is related to the recombination rate. So diffusion length and recombination rate are related, right? Let me highlight this guy right here. Then I'll make a comment that diffusion rate and recombination rate, they're like, or diffusion length rather, not diffusion rate. So a low recombination rate will give a long diffusion length. And the electron and hole effective masses are small and balanced. So just a word about that. I mean, the the mass of an electron in a material and the apparent mass of the hole, they're not like as light as they are in free space, like in a vacuum. And so it's basically, it has to do with their the rate at which they'll accelerate in an electric field. So the effective mass is just the mass that's measured in the material. So we don't have to understand this in any deep way. Just that this is the mass that's measured in the material. Okay. Oh, and also because it has a sharp absorption band, it can recycle photons, right? So photon recycling is where an electron hole pair is created by light, right? And then it collapses and it emits a photon, and then that photon is reabsorbed and makes a new electron hole pair, right? And every time you make a new electron hole pair, you increase the odds that it can be collected to do useful work outside of the device. So so that's also a good thing there. So dissipationless absorption. I call that elastic. It's an elastic process. So dissipationless is also, there's no Stokes shift, right? Okay. So they're high quality halide semiconductors, you know? So who knows, you know, maybe we can make photovoltaics with them, maybe we can make electronics with them. I do not know. But one of the things that I'm not really clear about and it's probably in this, or it's probably pretty obvious, is how you make the P and the N type MaPbI3 materials. Like, do you dope them with more lead, or do you replace iodine, or you know, I'm not really sure how that's done. How you make the P type and the N type. But it could be just different cations and anions in there. So anyhow, I think that's all I have for today. Thank you guys very much for indulging me in a little bit of baloney using MMA, and also listening to my boring talk that I gave to Balaz, and then my brief introduction to this paper. Read through it, see what you can understand, what you can't. Come to me with some questions, maybe Thursday or next Tuesday, and then I'll take your questions and we'll answer them. If I can't answer them right away, I'll drag them off and beat them to submission, and then serve them back to you.
Thanks, Atsu.
All righty, thanks guys.
Thank you.
Thank you.
Excellent day, excellent day. And I'm going to read your papers this weekend, so thank you so much.
Thank you.
Bye-bye, thank you, thank you.